Okay, folks, let's continue. Today is going to be moderately interesting because we will be getting things that are directly related to chemistry. And those things are optimization. That is maximizing and minimizing things, which can be, for example, chemical yield, unproductive reagent loss, or the probability of some disaster, or any parameter, generic parameter of physical or a chemical system that you are designing or trying to improve. Now, it is possible to do optimization analytically and numerically. Analytical methods are today, and numerical methods you will have in a couple of lectures. But let me give you a simple example. So let's say we have a reaction, and we're doing, I don't know, something like a fourth-year project. And any reaction would have a parameter called yield, which will be a function of all sorts of things. Initial concentration, reaction time, temperature, pressure, the volume of the vessel, and such things. X, Y, Z, and so on parameters. At the same time, there will also be loss, the unproductive waste of reagents, which will be a function broadly of the same parameters. X, and so on. And a typical optimization problem is to improve the yield to loss ratio. And we need to maximize it. Because if the yield is high and the loss is low, this number is big, and if it's the other way around, then this number is small. So how do we do something like this? Well, let us first formalize the problem and look at what it means to have a minimum or a maximum. If we plot some generic graph of a function, so let's say this is x, and this is f of x. So I'll plot something like that. Then we can identify visually that this example function has a minimum, a maximum, and what is called in mathematics an inflection. Now what happens at a minimum is the function that was previously dropping, so its rate of growth was negative, stops dropping for a while and then starts rising. So the rate of growth at this point is 0. So if I draw a tangent line to the function at this point, the tangent line is horizontal. So at this point, f prime of x is 0. The same happens at the inflection point, where the tangent line briefly becomes horizontal, and the same happens at the maximum. So actually, if we're looking for minima and maxima of a function, we should start by looking at the places where the derivative is 0, because those are the places where the function doesn't grow or drop, and those are perhaps the places where something happens. Either the change in sign of the growth rate, like it happens at a minimum or a maximum, or a temporary pause. In the long run, we are probably not interested in the inflection points, we are interested in maxima and minima. And so actually, so item 1 on the agenda, so optimization. First item is univariate. Is about finding locations where the first derivative is 0 and then classifying those locations into minima, maxima, and inflection. Let's go a bit more specific, and let me give you an example of a simplified optimization problem that you would have in chemical engineering. We are told that we need a reactor, a cylindrical reactor, with a volume V, which is fixed, and by the requirements of the engineering that's involved in there, and but whose radius is varying. So this radius we can vary. The reactor can be either very tall, but then it would have to have a small footprint, or it can have a large footprint and consequently have a smaller height. So this will be our radius, and this will be our height, and the volume is fixed for us. What, however, isn't fixed is the price. And we are told by the facility manager that corrosion resistant steel is very expensive. That is, he says, I need that volume in the reactor and I need it for the smallest possible price. So how do we minimize the cost of that reactor? Well, if we look at the volume, we know what the volume of the cylinder is. It's 2 pi r h, right? So the on a pi r squared h, which was the area of the side squared h. So the area of the bottom multiplied by the height. So that is our volume. Corrosion resistant steel is sold by the square meter. It's rolled steel, and so our price is going to be proportional to the surface area of this cylinder. So the area will be the top and the bottom, so pi r squared times 2 plus the area of the sides, and that is 2 pi r times h, so the circumference times the height. And this is what our price is going to be proportional to, and we need to minimize this. Okay, well, our h and r are not independent, they are linked by our fixed volume. So our h, for example, would be volume over pi r squared, and I can replace h in here. So our h will be 2 pi r squared plus 2 pi r times v squared. A few things cancel. So 2 pi r squared plus pi cancels, 1 unit of r cancels, 2v over r. And we need to minimize this. Well, we now actually have only one parameter that is variable in here, and that's the radius. So minimize with respect to r. Okay. Let's try and look at the stationary points. From that picture, we can conclude that we would like such points that make A prime go to 0. So those will be minima, maxima, or the inflection points. Our A of r is here. So A prime of r, 2 pi r squared prime, 4 pi r, and then minus 2v over r squared. That to be 0. Well, that's easily enough solved. We move that over here, so 4 pi r equals 2v over r squared, multiplying both sides by r squared, 2 pi r cubed, should be 4 pi r. 4 pi r cubed is 2v, which means that r is the cubic root of v over 2 pi. V over 2 pi. And obviously we want the positive version of that because it's impossible to make a cylinder with a negative radius. Okay, so we found a stationary point, but we don't actually know whether that point is a minimum, a maximum, or an inflection point. The last thing our manager would want is for us to maximize the cost rather than minimize it. And so we really need a secondary criterion here on how to partition our stationary points into minima and maxima. The best place to look are various standard functions like quadratic, for example. So if I draw a typical parabola, f of x equals ax the origin, that's x, and that's f. So f prime of 0 is 0, so it is a stationary point. And if we calculate f double prime, in this case f prime is 2kx, and f double prime is just 2k. So f double prime of 0 will be 2k, and that's greater than 0. If we look at the situation where we have a minimum instead, draw a function that looks like a maximum instead, looks like that. So this is f x minus kx squared. X. And in this case, f prime at 0 will be minus 2kx, still 0. 0. However, f double prime of 0 will be minus 2k. And it is less than 0. Okay, so it looks like second derivative provides a diagnostic criterion. If the second derivative is positive, we have a minimum. If the second derivative is negative, then we have a maximum. So let's write that down. Diagnostics. F double prime at some point x naught, which we have identified greater than 0, means min. F double prime of x naught less than 0 means max. What about the points then where it actually is 0? Let's investigate something like a cubic or a quartic, perhaps, function. So if I plot f of x equals x to the fourth, that looks something like this. A fairly shallow minimum in here. And in this case, actually, f prime of 0 and f double prime of 0 are both 0. So a 0 second derivative might indicate a really shallow minimum, or a really flat maximum, or in fact an inflection point like this. So in situations where f double prime is 0, the best way to proceed is to plot it. And there are various analytical ways, but none of them are particularly reliable. Essentially, for practical purposes, to you as future chemical engineers, if f double prime is 0, you probably want to avoid that point anyway, because things are happening in there where the second derivative is 0, and quite a lot of modern computational methods would get stuck at that point. It's possible. Okay, let's take a look at our cylindrical reactor. What we now need to make sure is that a double prime is in fact positive, that we haven't maximized the cost for our manager rather than minimized it. So, a double prime of r, differentiate that thing again, small I, and then plus r for v over r cubed, I think. R cubed, and we just plug in that r that we have obtained. So a double prime, let's call this point r naught, is 4 pi plus 4b over cubic cubed, so just b over 2 pi, and that's obviously positive. Because there are positive numbers in here, and there's a plus, and therefore we do have a minimum. So we go back and triumphantly report to the chief engineer that we have found a way to minimize cost. Now, this is a highly artificial scenario. We have assumed that, for example, steel truly is solved by the square meter, whereas in reality what we would have had to do is to buy a square that contains this circle and cut the circle out and discard the rest of the square. We have neglected the labor costs, we have neglected considerations related to the ceiling height in the building, that it's not actually possible to fit an arbitrary reactor because the ceiling height is finite, various other related things. So in practice, you would have various constraints associated with your optimization problem, and it's possible to incorporate those constraints. That mathematics is a bit more complicated. I've given you the link in the handout, so-called Lagrange multipliers in essence. But in practice, you need to check that the solutions you have obtained, the optima you have obtained, actually make physical sense, right? There's no point optimizing if the optimum point produces you a complex radius or a negative radius. Well, technically speaking, it's a minimum perhaps or a maximum, but practically such a thing is not realizable. So the bottom line for the minimization of univariate functions is calculate the derivative, then find where the derivative is 0, these are stationary points of the function, then calculate the second derivative at those points, and if the derivative is positive, it's a minimum, if it's negative, it's a maximum. If it's equal to 0, then plot and look and see what kind of point you have found. Now, the list that we've had here, minima, inflection point, and maxima, it is exhaustive for functions of one variable. For functions of two variables or more, things get considerably more interesting. Now, the second item today is multivariate optimization. Again, let us start with a bit of philosophy. Let's draw a function that clearly has, for example, a minimum, and then take a look at how it behaves as a minimum. Draw a coordinate system and some kind of function that behaves in some way, and we would like the function to have, for example, a minimum. So it is something that's roughly parabolic. So we can it will have a minimum. So very typical quadratic minimum for it. And that would be x, that would be y, and that would be f of x and y. Let us take a look at how this function behaves at the point where it has a minimum. In particular, let us draw some tangent lines at the point of that minimum. So in the direction of y, the tangent line will be this. So it's underneath, and it touches the function at the point where it has a minimum. And the tangent line with respect to x will do the same. Notice that both tangent lines are actually horizontal. That is, this function, if it's taken as a function of just y, when we keep the x constant, df by dy, it has a minimum, so df by dy must be 0. F by y is 0, partial derivative. If we look in the direction of x, that is, if we keep y fixed, then likewise the tangent line is horizontal. And so actually at the same time, df by dx. And so it looks like we have a generalization of our stationary point condition, that it's not that one and only derivatives that we had here, that must be 0. It must be all first partial derivatives of the function. Now it would not be possible to draw a function of 3 variables, there aren't enough dimensions on this board to properly represent such function, but you can see, for example, for a minimum, we have this. Now, a maximum would obviously be the same, it's just the entire picture is going to be flipped around. However, there's a twist in that in multiple dimensions, you can have functions that have both minima and maxima at the same point. So if we draw another function, slightly more carefully, because it's usually pretty hard to draw. We have it behaving parabolically at this edge and behaving parabolically at that edge as well. However, in the middle, here it has a dip. What is clear about this function is at this point here, if that direction is x and that direction is y and the perpendicular direction is z, up there, then with respect to the direction x we have a maximum. The tangent line's horizontal, and with respect to that direction, it's a maximum. So again, d f by f is 0. However, with respect to direction y, this one, we had a minimum. But again, the tangent line at that point is horizontal. So it would appear that for minimum, maxima, and these weird points called saddles, the criteria for the first derivative are the same, much like they have been for minima and maxima in the case of a function of one variable. What is different, however, is curvature. In this case, curvature was positive in both directions. However, here, curvature is positive in one direction and negative in the other direction. Curvature is the second derivative, and actually in this case, it will be second partial derivatives that will be determining the nature of this point. Now, once again, I'll give you a criterion for the second derivative. Here we could kind of illustrate this easily by looking at quadratic functions. It is not possible to illustrate it so easily for the functions of many variables, but let me give you a criterion for the function of two variables. So what you need to do, so I'd say 2.1, deciding the nature of the point. Now, the expression I'm about to give you has a derivation, but we don't have the time for that derivation, unfortunately. This is a short course. There are enormous modules, whole modules in the mathematics department, 2 of them, on the theory of optimization, and there they derive it at some point. If you do this professionally, you might find the derivation, but I will just give you it without proof. Obviously, I would not expect you to remember that if I have just pulled the rabbit out of the hat in here. So if you take f double prime with respect to x, so second derivative with respect to x, minus a certain number lambda, then f double prime y minus that same number lambda minus f double prime xy squared equals 0. And this is a quadratic equation for this number lambda. So solve the equation. And then if you have both lambdas positive, so lambda 1, 2 greater than 0, then we have a minimum. If lambda 1, 2 are both less than 0, then we have a maximum. And if the signs are different, then this is a saddle. And again, if either of them is 0, lambda 1 or 2 equals 0, plot and check. No better advice, unfortunately, that's available. So basically, if you are ever examined on this, this criterion will be provided within the text of the problem, and this as well. Okay, so we now know how to identify tentatively the stationary points of multivariate functions, and for two-dimensional functions we have the criterion for minimum, maximum, and saddle. So let me give you an example. We have f of x, y equals x minus 1 squared minus y minus 2 squared. We are told to find any such minima, maxima, or saddle points as may exist in this function. Well, we proceed by the recipe that we have gleaned from our artistic exercises here. df by dy, df by dx must be 0. So df by dx is 2x minus 1 minus 2. Then df by dy will be minus 2y minus 4. That must be 0, and that must be 0. And here we conclude that x is equal to 1, y is equal to 2 minus 2. We have a single solution because the equations are linear. If you have quadratic or perhaps logarithmic or exponential or sinusoidal equations in here, you will have multiple solutions. That means the function has multiple. Yes,
I think it's plus 4.
It is plus 4. Good job. Well spotted. So if you have functions that have produced multiple solutions for this system, then you will have multiple minima or maxima or other types of points. But our job now is to find out what this point is. Well, for that we need all the derivatives, and this is why I've been torturing you with the partial derivatives in the previous class, because they're actually useful in these problems. So, d2f by dx squared is 2. d2f by dy squared is minus 2. And d2f by dx dy, and you know that for well-behaved functions the mixed derivatives are equal, so d2f by dx dy is the same as d2f by dy dx, but they are both 0. Okay, let us plug it into there. So d2f by dx squared is 2 minus lambda. And d2f by dy squared minus 2 minus lambda And the minus mixed derivative squared, that's just 0, so this equals to 0. Well, thankfully, actually, the quadratic equation already came factorized, and so we can conclude that number 1 is equal to 2, and number 2 is equal to minus 2 in here, and therefore the stationary point is S0. And it's actually plotted in your handout. I fired up Mathematica and I produced a plot, and there you have it. Let's take a look at perhaps a more complicated example of univariate and multivariate optimizations. Partition our space here. Let us combine some functions that might be growing and other functions that might be decaying. So things, for example, like this. F of x equals x squared e to the minus x. In this situation, what you have is x squared, a function that grows, multiplied by e to the minus x, and that is the function that decays. At some point, because exponential decays faster than any polynomial can grow, it will overpower it and force it to 0. Let's see whether this thing, as we can tentatively predict, would have a maximum. So let's sketch it first. X and f. At the point where x is equal to 0, this function is 0. Then at the point where the x is in infinity, this function is also 0, so at some point it has to decay. However, initially it starts off growing and then eventually decays. And so we are hunting for this suspected maximum. Let's see if we can find it and determine what it is. Okay, f prime x will be 2x e to the minus x, and then minus x squared e to the minus x. So the standard product rule. Okay, this must be 0. Let's take a look at it. So then 2x e to the minus x squared e to the minus x equals 0. One place where this is 0 is actually infinity. Right? Remember your limits. The limit of that thing, because exponential fades at infinity, will be 0, and so one obvious solution here is x equals infinity. Then that thing we can cancel now, because we have accounted for it. So 2x minus x squared equals 0. The other obvious solution to this is x equals 0. And then if we cancel one instance of x, we will have 2 minus x equals 0, x equals 2. So actually we have 3 candidate points here for stationary points. This function is stationary at 0, stationary at 2, and stationary at infinity. Let's take a good look as to what actually happens at all of those points. F double prime of x is, well, differentiate that again. So 2e minus x plus, or as a minus, 2x e minus x minus 2x e minus x, and then plus x squared minus x. A fairly long expression, but nothing too complicated. 2e to the minus x minus 4x e to the minus x plus x squared e to the minus x. Probably best to take e to the minus x out of the bracket. 2 minus 4x plus x squared e to the minus x. That's our second derivative. Let's take a look. At infinity, we have 0, because that goes to 0 rapidly. So f double prime at infinity is 0. But from plotting the function, we just conclude that that's a terribly shallow, in fact, infinitely shallow minimum. So that is a minimum. Let's take a look at 0. Double prime at 0. Okay. That's equal to 1. That's equal to 0, 2. Greater than 0. Minimum. And indeed, if we plot this very carefully here, we will discover that does this. I think so. And then interesting things happen because that blows out into infinity as x becomes minus infinity. So if memory serves, it does this quite nicely. Moving on. But that's a minimum. And then finally, f double prime at 2 is, well, probably hard to say what's it going to be because e to the minus 2 is not a pretty number, but thankfully the exponential is always positive. And so we have 2 minus 8, so that's minus 6, plus 4, that's minus 2, so that's actually less than 0. And so it's a maximum. And so we have found the maximum we have been fishing for in this function. This maximum occurs at x equals 2. And we can plug it in, should we so like, and actually find out what the function is equal to at z maximum. So, similar things you will do in your practice during the class with univariate and multivariate functions. But let me just give you a practical flow chart that you as chemists will follow whenever you seek to optimize the sensitivity of a certain instrument, the width of a spectral line, the homogeneity of magnetic field somewhere, the yield of a certain reaction, the efficiency of a certain process, the probability of this particle being here rather than there, and so on. So, a flow chart. Item number 1, create system model. That is, you need to dig out the necessary equations of motion. In the case of chemical kinetics, the reaction rate equations. In thermodynamics, some kind of enthalpy, and so on. In electromagnetics, Maxwell's equations. In quantum mechanics, Schrödinger's equations. In general relativity, the electric tensor equation of motion, and so on. You create the model and you expose controllable parameters. Things that you can alter at will, like temperature. The second thing is to formulate a figure of merit. And the figure of merit is that which we seek to optimize. For example, cost. Or yield. Or some such. In terms of those parameters. Item 3, if we have our figure of merit, I don't know, f of x, of obtained candidate points. x1, y1, and so on, x2, y2, and so on. Much like it happened here, you will have multiple parameter combinations at which you have a stationary point of your figure of merit. So number 4, inspect second derivatives. Or do the plotting or do something and identify points of interest. So item number 5, report back to whoever gave you the task. And item number 6, profit. That is the general optimization flow chart these days in a great variety of areas. Actually, we published a few research papers on optimal control theory where all of that was related to getting a quantum system from point A to point B with the maximum possible precision. Now, an important caution here is that just like the proverbial jinn from, you know, the Persian fairy tales, this optimization will diligently fulfill your wishes. That is, if you've specified the figure of merit, it will maximize it. However, it will do it blindly and stupidly. That is, if your figure of merit is not well formulated, it will simply return a stupid answer. You will find many examples in the literature. So, a simple case would be getting your cylindrical vessel that doesn't fit into the ceiling height of your installation. Right? So it is actually a surprisingly difficult thing to formulate this figure of merit and the associated constraints. And perhaps there could be penalties as well. That is, if you are a pharmaceutical company, then you'll have to balance the direct pharmaceutical effect of a substance against the side effects, like nausea or dizziness or liver shutdown, or whatever it is that, you know, modern medicines occasionally do have. If it's a cancer drug, well, that may overall be beneficial in that the patient will die next year rather than next week, but you have to take into account the toxicity, and that would be subtracted from your figure of merit, whereas the therapeutic effect would be added to it. Okay, so the summary of the lecture: you will encounter throughout your entire career as chemists the need to maximize and minimize certain things as functions of the parameters you can control. Trivially, for a function of one variable, you can see that minima and maxima are points where the derivative is 0. So formulate the model, differentiate, put the derivative to 0, find the candidate points. Minima and maxima differ in the sign of the curvature, which is the derivative. Positive curvature means the minimum, negative curvature means the maximum. Calculate the second derivative, inspect its value at the points of interest. If it's positive, it's a minimum, it's negative, it's a maximum. The best thing to do in the case where it's 0 is to plot and look. By the same philosophy, you can extend this to multiple variables, not just 2, 3, or more. We routinely do a couple of million-dimensional optimizations in the research that we do. And then inspect the first derivatives, find the points at which they're 0, this is the points of interest. Then inspect the curvature, either mathematically or graphically, find out whether it's a minimum or a maximum. And these are a couple of simple examples that you will have more of in your practice classes. And the general flow chart for any engineer, for any scientist in general, I would say, is you start with creating a mathematical model of your system, and much of this course is about how to create those models. You make sure that your model contains the parameters you can control as its parameters, temperature, pressure, whatever it is. You decide what it is that you seek to minimize or maximize. It's called a figure of merit. You add to it all of that which is beneficial and perhaps subtract out of it all that is detrimental. Then you take the derivatives of that figure of merit with respect to the parameters you can control. You identify the points in the parameter space that might be minima or maxima. You inspect the curvature of your figure of merit, classify them into minima and maxima, pick whatever it is that interests you, and hope for the best. That's all I have to say. Any questions?